Partial derivatives. That's my favorite topic, actually, and usual students like it as well. Partial derivatives. So, this is such a bad handwriting. Okay, remember, I'm not an evening teacher, so keep an eye on what I'm saying and let me know. Example number 1, f of x is a natural log of x plus a square root x squared plus y squared plus z squared. Good. And then they're gonna ask you, on the exam, you will have like 3 or 4 questions, quite a lot, I think 4, about partial derivatives. So prepare all of them, including chain rule and not chain rule. This is not chain rule here. Partial derivative with respect to x looks like this, or delta, but with tilted kind of head, partial derivative f with respect to x like so, or sometimes you will see it like so. This is actually not a popular one. So these two are the most popular notations for partial derivatives. This one known around the world. That means here you use chain rule, but not the multivariable chain rule. For now, it's just a simple chain rule. That means you are taking the derivative of the function outside, which is this whole logarithm. I can see it's a logarithm of something, right? That's how I teach calculus 1, logarithm of love. What is derivative of logarithm of love? Well, remember, it's 1 over love, so you need to copy everything inside without looking at it first. My students, remember, I'm teaching it as the Russian dolls because they are nested inside of each other, times, so it's like so. 1 over love times love prime. So this love prime now is partial derivative because now you know derivative with respect to what matters. So this is derivative with respect to x. Okay, so I'm taking derivative of this whole piece inside of the log with respect to x. That matters. So that means I'm treating only x as an important guy, a variable, and all other variables are not important. They are constants. So every time I see them, I know that they will be treated like constants. So x matters here. It's the only variable here for this specific case. Derivative of x is 1 plus square root is also chain rule. We know the derivative of the square root is 1 over 2 of square roots. Check it if you don't remember that. X squared plus y squared plus z squared. That's basically square x to 1/2 becomes minus 1 over 2 x to the, like so, becomes x, what is going to becomes 1/2 x to the minus 1/2, like so, there. Times, and to save space, I'll put it in the numerator, derivative of the function inside of the square root, which is, again, x squared gives you 2x, y squared gives you 0, z squared gives you 0, and that is the answer. And you don't have to simplify it. Well, I would cancel this out. You can type it in like this, and it will accept the answer. I looked it up. So that is good. Why are you guys seeing? Yeah, let me check. Are you seeing this? Okay, good. And now guess what? I will just do one more, but you should practice all of them. Derivative with respect to y will be exactly the same thing. 1 over love, so that's the whole thing over here, times derivative of love. That's the function inside of the log. But this time, derivative of x is 0 because x now is treated as a constant, while y is now a cool guy. Here it is. Y is treated versus x as the variable, and it's the only variable here. So it's going to be 0 plus, again, 2 of the square roots times, and you copy each time the square root, times x squared gives you 0, 2y plus 0. So this is like, if you get this part, you become very fast at this. And f and z, same thing, do it yourself. Yeah, what do you feel about this? There will be several questions like this. So if you're good at this, those are good points, to be honest. That's why I like them. Oh, there's some questions in the chat. Okay, people discussing that. Review later. Thanks for doing this. Okay, good. That's good. Ah, I see. Not allowed any candy and coffee until they graduate. Very smart. Interesting. So, yeah, that was a comment about how to stay awake. Second derivative. Well, guess what? We can also, example 2. Second derivatives. As you remember from calculus 1, there are more derivatives than just first derivative. So we will ask you to practice that. And now you know second derivatives have lots of applications. Actually, if you are in engineering major and biology major, you will see that second and third derivatives have lots of applications in real life. They're not only densities, but also the speed of acceleration and those kind of things. Aerodynamics, yeah, I remember. So, and so on. So you will be fascinated. But in math, as you can see, it already has applications. It already helps you to find maximum and minimum using second derivative test. Pretty cool. So what is second derivative with respect to x and x? How do you see that? You're supposed to see it only one way. You differentiate with respect to x, and then again with respect to x. So that's how I see it. And then there was a very smart question in the forum that the order is weird with this kind of notation. So check out my answer. You should see it as an order of functions, function of a function. Let's find the first derivative, cannot go over that. So this is a very good example. It checks how your vision is being trained, how your vision is being trained to see important things and not important things. That's why I'm making a joke that with math people become like Neo from the Matrix. We see things around lots of numbers and variables. For example, in this formula, I see that x is important, while y is not important. Y is a constant. Y can be like 17 or pi or e, but it's not a variable. So with respect to x, I can see x is important, and it's going to be 12x squared y. Agree? Because derivative of x cubed is 3x squared. Boom, done. Minus 7y squared. Agree? Because x is the only variable. Minus 7y squared is the constant. Now, ignore the original part. Put this in the box. Putting things in the box helps a lot to organize the information, especially for these kind of problems. And now, they ask you to find second derivative. Where to look? Look at the first derivative. What kind of first derivative? What if you have a whole list of them? This first derivative with respect to x, and you again see x as a variable, and only x is a variable. 2 times 12, 24. 24xy minus 0, because there's no x in the second part. What if I want to find mixed one? xy second derivative. Then again, where should I look? I should look in the box I just created. Maybe there are many of them, but you need to look for this one. And now differentiate that box with respect to y. So now my brain have to switch pretty fast. Imagine you have 15 variables. Your brain needs to be trained that finally not only x and y are important. X, y, t, g is gravitational forces, w, v, velocity, m, mass, and all of those variables. Think about that. Your brain have to be good enough to switch. Now my brain is switching. Y is important while x is a constant. If y is a variable, then 12x squared will stay. Y prime gives you 1 minus 14y. Agree? So I'm telling you, somehow it's my favorite topic. My imagination is really good when it comes to switching things between each other. And that's why I see it so clearly. I think it comes from practice though. Now to get other derivatives like y and y or y and x, I need to first find derivative with respect to y. Where should I look? Into the very original function. Here it is. Let me erase the blue color. You can actually rewrite it, and if you like color coding, then use color coding for color coding what is the variable. Maybe that will help you. So now I see y as important guy, and then x is not important. So derivative of y is 1, so it's going to be 4x cubed. Derivative of y squared is 2y, so it's going to be minus 14xy. Agree? Differentiating with respect to y. Putting this in the box. Let's make a pretty one. Now it's the second box now. So this one. And now if I want to find derivatives like fyy or fyx, I know where to look. I will be looking where the first derivative was taken with respect to y. So if I want to do it with respect to y, again, it will be 0 minus 14x, because y survives, y gave you 1, 14x survives as a constant being multiplied by a variable. If I want to take derivative yx, where should I look? I should look at the same place, but now x is the variable. It will be 12x squared minus 14y. And as you remember, for nice functions, for good functions, and in this class we only work with these two should be the same. xy matches with yx for nice functions. And the definition of nice comes in the upper level classes. Smooth, continuous, with no holes, connected, those things you will learn later. Derivatives exist. That's actually the most important one. Product rule, we're gonna do that. My examples are coming. Brace yourself. Hey, people are asking for my examples. They are coming. Extra question for you. Extra question for you. Either yell or post it in the chat. What is the derivative of x with respect to t? Oh, that's like a tricky question. It's not going to be on the test, but I like to teach you to kind of improve your understanding of the situation. Okay, what I said means I need to look for the yellow box. Yellow box is here. I'm taking this function and differentiating with respect to t. What do you think the answer is? Everything is a constant, so 0. Exactly. So you should understand that if I'm introducing one more variable, which is why not, one more variable show up time, 4th dimension, 5th dimension, 7th dimension. With respect to that dimension, all that function is a constant. How fast is the constant in that dimension? 0 fast. The steepness is 0. So that is the idea. And then what is derivative of yx? How about that? That's a third derivative. Minus 13. Good job. So I looked over here, and then I looked over here. Y was already taken with respect to x, minus 14. If I do it with respect to y, that is 0. So on, just like to have some understanding here. Good job for that. You see that. That is very good. That was my example number 2. Number 3 and 4. F is x plus y plus z. I wanted to skip this one. Why? I think because it shows up again. Oh, it's fine. Let's do it. F, not prime anymore. That's fine. Let me do another notation for you to get used to it. Derivative of f with respect to x. What is that? There's like 3 variables here. So this function depends on x, y, and z. This is a 4-dimensional object. It takes in 3 dimensions, x, y, and z, which are here, a point in 3 dimensions, and spits out a 4-dimension. For example, density. Like here's the balloon, or even say, I like making examples with the human body. So your body, you're standing like so. You are a 3-dimensional object. Here you are, an alien. Okay, that's like, this is Cackles 3 students preparing for the exam for several days. You're a three-dimensional object. You have X, Y, and Z coordinates for every moment on your body. So do you understand that at any place on your body, the density inside you is different? Density and the pressure inside of your brain is not the same as in the lung or stomach or your hands and bones. So the 4-dimension maybe is just one more quality of your body, which, or I would say quantity or specification. In this case, I'm taking an example into the density. So over here, you add XYZ point, and it will spit out the density. Or temperature of the body is not the same everywhere. So here, temperature will be not the same as here. That's the basic example of 4-dimensional object and problem. Yeah, very nice application. Anyway, you see there's a quotient rule, and you should practice quotient rule. It's your favorite one, quotient rule. The way I'm teaching quotient rule in my classes is U over V prime. You don't have to follow the same shape, but I like it. I always start with squaring the denominator, not to forget to do it later. And then U prime V minus U V prime. Minus is important, order is important. Then, let's do it. Quotient rule. Well, first, is it a quotient rule after all? So that's also a question. Is everything, whatever is a fraction, should be called quotient rule? Not really. For example, derivative of 5 over x, is it a quotient rule? No, you can rewrite it somehow. Derivative of x squared over 7, is that a quotient rule? No. So apparently it depends on which function we're differentiating with respect to. If I'm differentiating with respect to y, definitely that will be a quotient rule, because y will be both in the numerator and denominator. Then it means there's a function divided by function. With respect to x, actually that's not the case. It's actually x plus y, which is a function multiplied by y plus z to the minus 1, which is a constant prime with respect to x. X is the only variable here. So based on the chain rule, first the constant survives, so this 1 over y plus z, that's a constant. So it will just stays like it is. And then derivative of x is 1 plus 0. Yeah, looks good to me. I just checked another way, and in my mind, the answer should be the same. Yeah, that's what I was thinking too. That's the second way I was thinking. Very good idea in the chat. The second way is to see it as x over y plus z plus y over y plus z with respect to x. Then this whole thing is constant. So it will be 0. This is constant. So the answer will be 1 over y plus z, which is the same thing. Yeah, good job. But if it's done with respect to y, then it's definitely a quotient rule, and you have to kind of be bothered by this. So squaring the denominator, differentiating the numerator separately. X prime gives you 0, y prime gives you 1. Copy the denominator. Minus, copy the numerator. Times derivative of the denominator, y gives you 1. And then z gives you 0. Cool. You can simplify that, and then you'll see y minus y, and then it goes away. Z minus x stays. And so on. So practice that. You see, the material is the same. Your brain just needs to say it out loud. If you want to, you can talk to yourself during the exam. I accept that, actually. I put a check mark on the honor log to say that it's okay to talk to yourself, because it used to be against the rules, but I never liked it. People should have rights to talk to themselves during the exam when they think. What if chain rule is involved? Pum, pum, pum. Chain rule. So this problem actually has a deeper meaning. If you add chain rule here, f is x plus y, y plus z, but each function is also a function. X is P plus 6R plus 5T. Y is minus 6R plus 5T. Okay. Z is P plus 6R minus 5R. So that is the idea of the chain rule in the 3D or upper dimensional cases. There's lots of illustrations how you can do it. I can show you the illustration later, but I can teach you the way you can do it fast. I learned to do it fast, and since then I never lost this ability. So I'm kind of very happy about this. So I will teach you and see if you like it. And then I will show you more explanations. Maybe you like different explanations. So when you want to differentiate, now we can ask, so you should understand that X and Y and Z, they have functions inside of them, right? So you should know, now we can ask you to differentiate with respect to any of those functions. And it seems like all of them depend on 3 different functions, maybe even 4, maybe even 17. So each of them, the way I see it, is a pocket that's hiding something inside some other variables. So this is how I usually explain in my class. And this is how it's you can visualize. If this function represents your pens and they have different pockets, without chain rule, you just have, in this case, 3 pockets, X, Y, and Z, and there is nothing inside. That was simple. They ask us to differentiate with respect to X. It means you need to just open one pocket. That's it. Here, each pocket might have 3 different pockets in the pocket. So now you have different choices. If they ask us to dig into the pocket code R, that pocket R can be here and here and here in each variable. So to get into the pocket R, you will have to differentiate with respect to each variable and dig into deeper one for each separate case because it's everywhere. So let's do that. It's easier to show, I guess, and talk at the same time. A, let's find partial derivative of f. Again, I can ask you with respect to x. That will be the same answer as we did here. And why not? I can actually ask never to go that deep into the pockets. And that may have some meaning, okay, in applications. But then I change my mind and I decide, you know what? Let's find what's happening with the pocket P. So how fast is the function f, which might represent density of your body, like I already mentioned this example, changing with respect to P. Maybe it's amount of medicine you're taking. Very good idea, actually. Equals. I don't even see P here because P is a hidden pocket inside of X, Y, and Z. To get into each pocket, I had to first differentiate the function with respect to X, differentiate the function with respect to Y later, differentiate the function with respect to Z. Each of these derivatives will have 3 pockets, and I'm choosing P to open. So I will have derivative of X with respect to P. As you can see, it's also partial derivative because X depends on more than just one variable. So that is the idea. And then Y is also with respect to P. And then Z is also with respect to P. So this is how I see it. Visually, I'm going to open pocket X, and pocket X opens pocket P. So it's like so. It's like so. And that's what they show in the book, if you remember. F, X, Y, Z. And then we have 3 variables, and they show it like so. PRT, PRT, PRT. So that's what I'm calling kind of the idea of opening pockets. If they want me to dig into pocket P, I have 3 different passes to check. Derivative of f with respect to x, and then derivative of x with respect to p. Derivative of y, derivative of f with respect to y, and y with respect to p. Derivative of f with respect to z, and then z with respect to p. So see the English language here. I say and that is product. If you take pre-calculus class, you know that. And means product. Or check the other pocket. That is addition. And or and. Because it's either pocket x and then p, or it's pocket y and then p, or it's pocket d and then p. Does it make sense? This is how I see it without memorizing any formulas. As you can see, I just wrote down the formula without checking my own notes because I never memorized it. Too much memory taken away. I need that memory for important things, okay? Like what my favorite chocolate and stuff like that. So I didn't memorize it. I understood it. And that's helped me personally a lot. And now just technically, I usually don't even write this formula, to be honest. I don't even remember writing it down when I was a student. I just jump into calculations right away. So I write it down for you. But can you do differentiation without this formula? I think you can. Let's see. So not seeing the formula. I'll write down that f is x plus y, y plus z. I'll just make it a smart way like so. If you don't remember the formula and then maybe you blank out on the exam, like, oh my gosh, without the formula, I cannot do it. I think you can if you understand the idea of these sub-pockets inside of the pockets. Let's try. So there's no formula. Let's just do the whole thing right away. And this way it's faster. Partial derivative of f with respect to x, no, with respect to p, we're digging into p, is, I'm looking at the function, let's call it star, function f. We're differentiating f with respect to x first, just in order. Okay, derivative of x, derivative of f with respect to x is going to be, we already agreed that it's maybe convenient to rewrite it as x y plus z plus y plus z. If I'm differentiating it with respect to x, it will be 1 over y plus z. Y plus z is a constant. X gives you 1, and the other half of the formula is 0. That is derivative of f with respect to x. But that's not enough. We need to go dive deeper and to differentiate formula number 1, let's call it number 1, with respect to p. And p is here as a main character, which means it's a variable, and others are constant. Derivative of p is 1. Or let's go check another big pocket. Another big pocket is called pocket y. Let's differentiate original function with respect to y. We did it over there, see? So it's a quotient rule, y plus z squared, 1 y plus z minus x plus y times 1. Now let's go and look at the formula. So this was formula number 1. Let's look at the formula number 2. Formula number 2 takes this y and opens the pocket and goes into the deeper pocket. Look for variable p. I don't see it. So that's 0. So the whole thing actually is 0. Who cares? Plus, now there's a third option. Variable z also has subpocket p. So to get into that subpocket p, let's differentiate f with respect to z. It's also a constant, but now in a denominator. Chain rule, yeah. X plus y is a constant. X plus y times y plus z to the minus 1 minus 1 over y plus z squared times the derivative of the function inside, which is 0 plus 1. That is just derivative of the function f with respect to z times, let's go to the formula number 3. That's the connection between Z, P, R, and T. Fix this to T. This one, why it's repeated. It's not R, T. Let's differentiate with respect to P, and that is 1. And that is the answer. How about that? That's the last example I wanted to show about chain rule and move on. But if you can do that, you can do lots of problems in the exam, to be honest. So this is a good chance to ask. Then we scroll and see partial derivative, second order, and then chain rule. Okay, that seems like to be good. Oh, and now there's a formula, as you can see. Now you can compare with the formula what we did. Outside derivative, inside derivative, or outside derivative, inside derivative, or outside derivative, inside derivative. So it's still chain rule. Now it's just have some visualization, which one is inside of which one. Good. Gradient and directional derivatives. Let's see that. Let me know if the sound is not good. Gradient and directional derivative. Yeah. Gradient has a formula. If they just ask you to find the gradient, then you find this thing called del. Del, very nice notation. Del F. Del F is just a list of partial derivatives with respect to F, with respect to Y, with respect to Z, with respect to T time, with respect to G gravity, with respect to density, pressure, you name it. So as if there are 75 dimensions, there'll be 75 partial derivatives, first order. So gradient was created to conveniently collect all these partial derivatives where they keep asking us to find this one, and more others. Gradient. And then they end up to understand that gradient actually has lots of applications because derivative have lots of applications, as you know already, in 2 dimensions. Then collection of all positive derivative have lots of applications, and they mean lots of stuff. Example number 1, let's keep the order, it's number 5. So find, oh, that's not the writing. Find the directional derivative. That's going to be on a test. I don't even have to hide this. We always put directional derivative on a test. Find directional derivative, and then we're going to throw it to a function x arc tangent of y over z. Then we give you point at -8, -8, -8. But now it's not just derivative. If I don't give you anything else, that's just derivative. So what's the difference between directional derivative? Directional derivative has a direction in, it's a vector, in the direction. And we give you a vector. Let's call it v, -10i plus 7j plus 7k. So the answer, well, you'll see actually what will be the answer. So directional derivative. You need to remember the formula. Solution. The formula has a notation. Capital D, that's directional derivative. Direction towards u of the function f. What u? I never gave you u. So u here is this directional vector they gave us, but we don't want to include the size of that vector. It messes up the idea behind the directional derivative. We just want to know the direction. So you should understand the vector has size and the magnitude. Remember the joke, right? If we just care about the direction, we don't need it to have any size except 1. So we're gonna shrink or stretch it to be unit, just to keep the direction. That's all the information matters. V over size of V is the unit vector of V, and let's call it U, like so. And all of those are vectors, of course, like so. And the formula for that, I kind of was supposed to write down the formula. That was more important, not just notation. Capital D, directional to U of the F is derivative of F. What kind of derivative? F might have 75 dimensions. Derivative with respect to all of them. And that's gradient. Gradient is the collection of all possible derivatives. Product with U. What kind of product? Scalar product. Who remembers the better name for that? I don't think it's better. It's a dot product in English books. A scalar product. Unlike the scalar product, scalar book product name is more useful and used in Europe, but I think it's more useful because then now you know the answer will be a number. Because dot product gives you a number, while cross product gives you a vector. So now you see the steps. Step 1, find the derivatives. Step 2, unitize the vector they gave us with the direction. It has some kind of size, we don't like it. And then find the dot product. 3 steps. Step 1, what is the partial derivatives of this function? First derivative with respect to x, then derivative with respect to y, and then derivative with respect to z. How do I know? Because I see all of them, x, y, and z. With respect to x, that is the best one. With respect to x, it's just x times the constant. So only the constant stays. Arctangent y over z, it's a constant. Now, comma, vector. With respect to y, we differentiate the function outside, which is arctangent times the function inside, which is a fraction. What is the derivative of arctangent? Who remembers? 1 over 1 plus input squared, y over z squared, times, and I'll save some space. Thank you. Times chain rule says. Remember you thought chain rule was hard? Now it's hard in 3-dimensional cards. So I'm teaching chain rule next week for my calculus 1 business students. They don't know how much they're gonna solve. Derivative of this function is a fraction, but with respect to what? With respect to y, it's just y times a constant. So it's gonna be 1 over z. Derivative of y is constant, 1. No, derivative of y is 1. Derivative of 1 over z is 1 over z. That is the second derivative. That is not the second derivative. It's derivative with respect to y. And with respect to z is the most annoying one. 1 over 1 plus input squared. But now input is a fraction where the variable is in the denominator. It's fine. It's just going to be minus y over z squared. If you wanted to speed up, this is the answer. Now you feel like, oh, that's a lot of type in your homework exam and stuff like that. Luckily, I think that is why they gave you a point. It just will be faster to type in. So plug in your point. Basically find the slope, right? This is derivative, but at the point, 1a. Yeah.
Question, Julia. Shouldn't the x be carried over for each one of those partials for the partial of y and partial of z?
See, I was checking if you guys are paying attention. Thank you so much. See, my x disappeared because it was blue. I ignored it. X should be carried because it's a constant. So copy it here and here. Thank you. Very good catch. Now, plug 8. This time it's easy. All of them are 8 minus 8, which is kind of not fair. If they're not the same, I highly recommend to sign them. X is here, Y is here, Z is here. Visually, brain likes seeing these connections, and then you can match them. But in this case, they're all minus 8, doesn't matter. This is notation minus 8, minus 8, and minus 8. That's a point plugged in into the vector. Will be arctangent of 1, very convenient. 1 plus 1, also 1, and just, no, wait, a minus 8, that's not that easy. And then 1 plus 1, so that's 2. Okay, good. Times minus 1 over 8. I should check my notes not to mess up. And then minus 8, that's 2. Minus 1/8, I think. So anyway, and now it's easier to type in. You can also keep simplifying if you want, but now you can type in there if you have A, B, C, D in your exam, because you will have, some of them will have steps there to give you partial credit at least for each step in case you mess up at the very end. That was this step, find the derivative. Now we want to multiply it by a vector v, but maybe it's not a unit. So let's check that. And instead of checking, just to make, usually we don't give you unit vector. I don't know why. Just to make it more trouble, u should be created from getting rid of the size of the v vector. If you don't like the way it's written, you can always rewrite it as minus 10, 7, and 7. Some students prefer this way or that way. Yeah. Then v is minus 10 and 7 and 7 divided by a square root of 100 plus 49 plus 49, which means every input will be divided by this number. 100 of 96, 196. Oh, that's a good number. So I don't trust myself, so I'm thinking I should check. But you check as well. Directional derivatives. And now you do a scalar product. I just want to check something really fast. My notes. And move on. It looks good to me though. Tangent planes, partial derivatives. Oh yeah, now we should not forget to review this. We did chain rule, that's good. Gradient. And this stupid problem. Yeah, looks very good. Looks very good. Okay. And now, so minus 10 and blah, blah, blah. And now 3, last step, you multiply. F times U. That is a product of two vectors, but it's what kind of product? Scalar product. So basically you just multiply this constant by this constant plus this constant by this constant plus. It's a product of corresponding components. You could actually write down what is arctangent of 1. It's a number, actually, it's a pretty good number. It's pi over 4, but I can write down for you. But if you don't have to. I noticed it actually accepts just typing it in. And if it doesn't accept, you can always email me and I will accept it as a full credit. Fine by me. If it's correct, though, make sure it's correct. And the answer should be a number. And the number is in front of me, which is minus 5 pi over 2 square root of 198. And negative directional derivative means something. So decreasing towards that direction. Derivative, gradient has lots of properties. That's why you were reading and listening about gradient ascent and gradient descent, which has lots of cool animations, which I should show you, all I will post in the internet, about when you have a mountain and then you drop a ball, where it's going to go. Depends where you're going to drop it. If you drop it over here, it will go one way. If you drop it over here, it's going to go this way. So that's exactly the idea of the directional derivative as well. Derivative means where will it go? Towards over there. So not only point matters, minus 8, minus 8, minus 8. That's a point in three-dimensional Cartesian coordinates. But also direction. Over here will be one pass. Over here will be another pass. Over here will be a waterfall, for example. And now this means it's descending, going down. So, well, it's one of the applications actually. Okay, move on. Find the direction in which the maximum rate of change occurred. Okay, good. That was a very classical problem. I remember we had it in our exam in 4.6. Find the, and people messed up badly on this problem, to be honest. I will show you why right now, and hopefully you'll remember and don't do the mistake they did. Find the direction. Find a direction. Okay, let's make sure it's clear. Find the direction in which. That's the idea of this dropping ball. Find a direction in which the maximum rate of change of f occurs. Now we give you f and the point. So makes sense. The idea was the mountain repeats itself. I should show you the animation because it's just really amazing. Idea repeats itself. If the location matters a lot. So the point where you start all of this matters. Gradient descent. I forgot how to write it as always. Yes, SC. Images. It's pretty cool. I have to show once then to explain. Here you go. This is what they're asking. Not only the location matters where you start. Why starting here? Maybe you can start over here. Maybe you can start over here. But also matters the direction. Why some balls went over here, but other balls went here, and this one stacks over here. There's the properties of this three-dimensional surface. That's why. Same thing here. See, the ball is dropping down from this mountain. It matters where and why. So this is what they're asking. What is the direction in which the maximum rate of change occurs? Maybe over here? No. Who is walking? So if you say, let's go down this mountain, it's getting cold. You're not gonna go towards this edge of the mountain. That will take forever to go down. You're not gonna go towards up. That is weird. There should be the fastest way to go down, probably jumping off the cliff. Maybe you have tools for that, okay. But that is going to be the good example of the maximum rate of change. In this case, the maximum rate of the gradient descent, jumping off the cliff, kind of dramatic idea. But let's see. Yeah, this is my favorite one. I remember this one. This is a really good presentation. Not only it matters where you start, and that's why we give you a point every time, but this one just stuck. So this is not a very good rate of change. That's definitely not the maximum. You barely changed any location here. This one, yeah, you go down, but like slow. This is the maximum rate of change from this point. You went to the left a little bit, then down to the right. So these people will climb down the mountain the fastest, while some people will go up, some people will go to the edge, and it will not be optimal. That is the idea here. And here, of course. See, pretty cool. See, they all have directions, and we don't care about the size of this directional vector. That's why we make it unit. We just want to see the direction of the directional vector. I think that's good enough. I think you got it. And here is the idea of the saddle point versus maximum and minimum. I will keep this animation for now, and I'll show you again. And that explains the difference really well. Let's write it down. So I give you a function, f. F is f of x and y is finally some trigonometric function. Let's practice differentiating this and the product way like you requested at 1 and 0. So again, don't be afraid if you don't remember what is sine of pi over 4. You can type it in carefully and then it will accept it on the exam. Answer. So you need to find the gradient, which is partial derivative with respect to x and partial derivative with respect to y. But then at the point, so the notation actually is nicely used internationally, a bar and then a point. That means at 0, 1. That is a vector, So when they ask you about the direction, they ask you about the vector. Remember that. That is a vector because direction is not a number. It's like over there. So there was a person who is, and people in the mountain, and then they ask each other which way we should climb down the fastest. Seems like it's going to get dark soon. And in one point's over there. So it's a vector. And we know how to do that. You just really fast find derivative, partial derivative with respect to x of sine. That's going to be cosine. Copy x times y times the derivative of the function inside, which is y. X gives you 1, comma, partial derivative with respect to y. Same thing, cosine x and y, but this time times x, because y is a constant. Plug 0 and 1. Again, visually for your brain. I'm claiming all brains are the same, but it's nice to sign it with a pencil. And now you can visually see x is correlated with 0. So match it. Okay, so this is 0. This is 1. You will have cosine of 0. What is cosine of 0? It's nice if you know at least cosine of 0. That is 1. Then what is this one? Since x is 0, this is 0. That is my idea here. Where did I get this example from? Anyway, but if they ask you to find, so question A. We answered question A. Find the direction in which the maximum rate of change of f occurs. Your job is to understand. They're asking about the gradient. Gradient shows you the maximum rate of change, maximum rate of change of the temperature, the maximum rate of change of the steepness of the mountain, and so on. That is the beauty of application of the gradient. Still have no idea where I got this example from. Since I did it in the morning, now I don't remember. Oh, I found it. Here it is. Question B is asking you this. And that's what my students I remember messed up, so I want to warn it. What is the maximum rate of change? Rate of change, blah, 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 of this function f. And what is the difference of these two questions? Find the direction. We found it. It says over there, 1, 0. It's literally on x and y. You know how to draw vectors. 1 goes to the right, 0 up. So it's like over there. The mountain decreases the most over there, or the temperature decreases the most on the table over there. So that's the idea. But how fast is actually happening? That means they want you to find gradient and now find the size of that. So gradient is responsible for the maximum rate of change. And then the size of that gradient gives you the maximum rate of change, which is the square root of 1 plus 0, which is the square root of 1, which is 1. Yeah, that's what I wanted to show. Don't mix up these two. Maximum rate is a number, while direction is a vector. I already wrote it down. Good. Cosine of 0 is 1, right? Yes. Point was 0 and 1. Point was cosine of 0 is 1. 1 times 1 is 1, and then second one is just 0. Move on. Let's go to your favorite topics, minimum and maximum. Y is not 0, Y was 1. That's why it's not 0, 0. That's why I'm saying write down with the pencil, so your brain does not assume everything gets to 0 or 1. Brain likes to have like simple things, so it's nice to force it to actually see these connections on a piece of paper.
No, in the original text of the problem,
oh,
it's listed as 1, 0.
Oh, this one I messed up. I see. Thank you. This one, it should be 0, 1. Okay, thank you. Interesting why I changed it.
Just rewrite the problem to fit the solution.
Yeah, that's what I do. that's how scientists get money. What do you CDC said it's gonna give money only to scientists who will solve the problems. It doesn't give funding to those who didn't solve the problem. Minimum, maximum.
I had a question about the max rate of change, though.
Yes.
So that's always going to be orthogonal to the contour, correct?
Yes. Mm-hmm.
And when you were giving the examples of the animations, you were talking about how one thing was faster than another one, but that the stuff that we're only going to be dealing with in problems is the max rate of change of a specific point. What is the direction at that point?
Yeah.
This brings up a little bit different question of, is there ever going to be a time of figuring out what the max rate of change across the entire surface is? Like, what point has the greatest max rate of change?
Not in this exam. I know what you're asking about. No, I did not see a problem like this there. I checked in the morning.
Okay.
That's a good question. But maximum minimums, I will cover right now application stuff and even graphs. So you will see it right now. There's all this wiggling control maps. So I'll teach you how to distinguish this, and hopefully you'll do good in the test as well. Let's see what's going on. It's easy to start with the formula. To figure out minimum maximums, apparently we need to find critical points first, right? Just like we did before. Critical points is where your derivative is 0. Just now it's more complicated because we have many derivatives. So which derivative? Well, all of them. And that's the idea here. So all of them should be equal to 0, gives you some critical points and stuff like that. And then you need to find second derivatives when the critical points are coming from derivatives equal to 0. That's what they call critical points, and DNA actually too, because something is happening there, so they are critical. And then we're building this determinant of the matrix. Second partial derivative xx, xy, yx, yy. That's a determinant of the matrix. Matrices are very important, actually. If you take linear algebra class, you'll see discrete math also has it. Matrices are the one who are used by Google Maps. When you ask your Google, okay, Google, how far it is to go to the Walmart, how does it know? It actually solves lots of matrices and finds the optimal way. Walmart Supercenter is at 800 East Southern Avenue, Tempe, Arizona. It is 1.9 miles away. So I actually did trigger it. So it does minimize the whole system and so on. That's pretty cool. I was also writing an article about this, so I remember that. F, X, X. So you cross multiply like so. There's a negative sign. Okay, enough. All of them decide to talk to me now. YY minus fxy times fyx, but for the good functions, they're the same, so you can square them. And now the sign matters. If this sign is negative, I cannot teach it. Something that told me very interesting. Negative means sad. So like so. It's sad, and because it's sad, it's a saddle point. But you can also ask me, wait a second, what do you mean negative? Isn't it a function? So yeah, you need to plug your point here. A, B, C, whatever is the point. So when you plug your point, you first calculate determinant, plug your point, each critical point, so one by one, and then see the sign. If at critical point number 1, it's negative, then you can stop your search. That is a saddle point because it's sad. As my students told me last semester. The next one, I am the one who teaching it this way. If at the critical point it's positive, then we don't know the answer. Right away, we have to check this guy, the first element of the determinant matrix, which is second derivative with respect to x and with respect to x. if that one is negative, let's actually do, yeah, negative, then which one is better? Let's do positive first. I think it's easy to remember that if it's positive, then it is smiling. My students know I teach it with a smiley face and grumpy face. Since it's smiling, what do you think? It's maximum or minimum? Well, look at the smile. It's over here. The tongue is at the bottom, so it's minimum. And then it's basically the opposite. If it's positive, it's minimum. If it's negative, then it's maximum. But if this guy the same guy end up to be negative, and then it's like this. It's kind of like, yeah, it's sad, but not as sad as saddle point. Look at the nose. The nose is maximum. And surprisingly, it helps to visualize. People actually really like it. See, some people have their, also get triggered by my voice. Alexa, what is my name? Yeah, I like when we're doing Zoom education, I like doing that, trigger people's Alexa and Zoom and Google sometimes. So this is the way you can memorize it. Let's do the examples. One of the examples we like to give is on the tests. Number 7 is when you don't have to calculate anything because it speeds up the process. So you should not freak out. If you see this, you actually should be happy about it. 8FY is 10 at 1 1. What is 1 1? And this is one of the few problems which you might have, which will be not filled in problem. It will be a choice. And now you have 4 choices. Did you know that you have 4 choices? Because I actually never mentioned the 4th choice. Minimum, maximum, saddle point, or the weirdest choice, which you might get on the test. Actually, I saw some of the options might get it. So it's randomized. Some people will get minimum, some people will get maximum, some people will get saddle point, and some people will get 0. And if it's 0, there's inconclusive. Inconclusive means use another test. There's many tests to test the critical point if it's next to minimum or saddle point. So just this second derivative test did not work. So you can answer inconclusive. That's the number 4 option. 4 options in front of you in yellow. Also probably should mention it's local. Local minimum, local maximum. So it's local peak of the mountain, and there may be many of them. So let's build this D based on the information I have. X, X, Y, Y, X, Y, Y, X. You see, they gave me numbers, so everything is calculated. 7, 10, 8, 8. 70 minus 64. Yes, minus 6. Minus 6 is negative. So it is set. And set means the point 1, 1 is a saddle point. A saddle point is a special point that shows up only in 3D because it's a maximum and a minimum at the same time. It's a maximum from this perspective.
Shouldn't it be positive 6?
Oh, thank you. I was thinking about it actually for a second. It is positive 6, but I wanted to talk about saddle point, and that's why I switched. So if it's positive 6, we don't know yet. Messed up my favorite problem. Okay, D is positive. Not enough information. Let's check FXX. FXX is 7, also positive. Both are positive. That is a local minimum. Agree? Because it's at the bottom of the smiley face. But I wanted to talk about saddle point. Maybe that's why my brain switched to saddle point. Saddle point is very interesting. When it comes to maximum, it makes sense. Here is my 3D object, it's maximum. When it comes to minimum, it also makes sense. Here's the bottom of the valley. But saddle point is literally a saddle on the horse. It is the maximum from this perspective. But minimum from this perspective. Because a horse saddle has like a deep depth inside, like so. So it's maximum and minimum at the same time. Anyway, it's easier to show this animation than to do it myself. Let's see. Conclusion. I came here for the animation. Where is it? Ooh, that is pretty too. Oh, I will show you contour maps right now. So this is actually a good example for that too. That's it. It just disappeared. Okay, fine. It doesn't exist anymore. Okay, I'll just show you this. Momentum. Yeah, it has lots of applications. Here it is, very pretty. So the idea is, you see, if you're a bug who is climbing from here down, the bug is going down the hill, and this is minimum. If you're a bug who is climbing up from the front, then it's a maximum. So it really depends. This is maximum and minimum from both sides, different sides. That's called a saddle point. Looks like a saddle, or chips. That's a chip actually. So as you can see, it depends where you're going to drop your ball. It's either stuck here because it's minimum, or it will drop down because it's a maximum. That is a pretty cool idea. Saddle point. And it only happens in 3D. So if you look at it from two directions, then it's obviously minimum or maximum. But in 3D, it ends up to be both. So we check out these. I have it in my notes, but still messed up. Funny. And then practice how to find the critical points. I will skip that because it's kind of calculus one material. So this step, practice by yourself. I can see we don't have enough time to work on this. So this one, practice. Make sure you actually know how to do it from the given function.
Do we have any that are going to be DNE? Do you know?
I don't remember. Can't say that fast. Just practice whatever you have in your practice review. Oh, basically my review file is really good. So this one should be good. No, but I don't remember anything. I saw some fractions, but I don't remember if they were about chain rule or maximum and minimum stuff.
Yeah, because nothing in the homework has been a DNE. It's all been.
Oh, that's fine. There were a couple of problems not from homework, and I deleted them. They were also super weird, so I deleted them. Now it's mostly from, I think all of it is from homework. Critical points. Yeah, I can see in my notes, I have nice functions with critical points. You find them, and now you start testing them using this second derivative test. Okay, yeah, my notes look really good. And how about this problem of check out the, is it here? Check out the problem of differentials, that thing. It's surprisingly very easy, but just kind of looks weird. I'll just write it down and you can check it by yourself. Differentials and the box problem, the volume of the box problem. Remember there was an optimal volume of the box problem. So that's the one I'm talking about. Check that one by yourself. That's one just like one step, but just not to freak out in case you see it. You might or might not see it. Because I want to move from here to iterated integrals. More questions about this before we move, because I'm ready to move into complicated stuff and it will take a whole hour, I already can see. So I want to go into integrals. Because differentiation, yeah, you can make small mistakes, but at least it makes sense. Integration is always harder. So I want to go to that direction. Let's check. Looks good. Okay. Ready or not? Problem number 9, actually 8. I think I mentioned 2 problems in once. Yeah. Iterated integral. Iterated. There will be lots of integrals there. And to be honest, they are doable. You just need to practice and not to freak out. I will try to explain right now. What do you mean? What do I mean? For example, 0 to 1 plus y, 10x minus 5y squared, dx, dy. First, I will just explain how to work with them, how to calculate them, and then I will explain you how to switch the order. That's the one that people stuck with, but I think I'm very good at explaining that. So let's do that. First, just at least know how to calculate stuff. That is already good. Double integral looks scary only at first until you hit triple integral. And then it becomes the like so. So that's going to be the third exam. But this is a 2-dimensional, 3-dimensional object. You're integrating with respect to one thing, with respect to another thing, and the outside, the answer gives you volumes. So those are volumes actually. Volume, let me first maybe write down, it is a volume for you to understand of the object below f equals 10x minus 5y squared and above the floor. And the floor has the shape above A. And A is written over here. So now I will explain you what it means. So it will be not a problem. I will explain better there. The idea, but the idea in 3D is we have X looking towards me. Come on, don't overheat. X looking toward me, Y to the right, and Z up, down, like so, like so. There's a curtain called F. Okay, that's a curtain. That's a 3-dimensional object. It swallows X and Y and spits out Z. So there's a curtain. Imagine a cloud floating in the sky. The cloud gives a shadow, like so, which calls a mapping. It's mapping onto 2D on the floor of X and Y. It maps on these 2-dimensional Cartesian coordinates, X and Y. And when it maps with a ray, for example, right, it also creates a shadow over here with some kind of awkward shape. Maybe the same shape, or maybe we decided, you know what, we don't care about the same shape. We want to make a restriction and make it only like a square, just because we decided. What is the volume that this object creates? The volume below the cloud, but with cutted, for example, box. The volume between the cloud and the box and the square, triangle, one more cloud, a smartphone on the 2D object. What is the volume between those two things? That is the idea. So triple integral, like I mentioned in the previous exam review, will be what is the volume of the 4-dimensional thing. Below that thing, we have shadow into 3-dimensional Cartesian coordinates. What is the volume of that? So that's where it's all getting to. Those are volumes. V equals. But anyway, outside of this idea, do you know how to just work with this algebraically? Let's call it algebra. So you first see it as one integral inside of another integral. You start with the one that is the most in the inside. So if you have 5 of them, you start with the X, Y, Z, whatever is inside. So leave alone the outside integral. It will have to wait for its order, okay? Then integrate the part inside with respect to X. That means your brain, again, should be very good in understanding that X is the variable and Y is a constant. But this time you're integrating instead of differentiating. So it will be 10x squared over 2 minus 5y squared x. Let me color code it. X, red color. Okay, thank you. X squared over 2, like so. Now there's a bar because it's definitely integral actually, and you have to plug those functions, y plus 1 and y, where to plug them into. We have like 2 variables here. Maybe you have 17 variables. You need to know where to plug those things. Remember, you differentiate with respect to x, so those functions belong to x. This is x equals 1 plus y and x equals y. So sometimes people actually sign them. When you have 5 or 7 different variables, you get lost. So some people actually sign them like this with a pencil. So now they know where to plug and not to mess up. And now it's exactly like we did before. Plug the top minus the bottom, see calculus 1. The end of calculus 1, we're doing definite integrals. The outside integrals keep waiting. The y's keep thinking what is happening here. Plugging into x. Top, x equals y. So it will be 10 over 2. I will keep it for now. And then it will be y squared minus 5y squared. Plugging y. Put parentheses minus. Plug the top. The top function is 1 plus y. 10 over 5. Why did I keep it 10 over 2? No. X is 1 plus y squared minus 5y squared times 1 plus y dy. Some people do it separately, so they don't have to have such a long, huge integral. They calculate separately, simplify, blah, blah, blah. And now you have to simplify and integrate with respect to y. And that's why integration is harder than differentiation, because with differentiation, at least some things would go to 0. With integration, yeah, good luck with that. The more you integrate, the more variables actually show up. So, yeah. Where does this problem came from? Why I keep locating problems I don't see anywhere? Hope I accidentally did not choose them from the Excel. That would be so wrong. I cannot find them, to be honest. They should be from the review. I'm not allowed to use any other problems outside of the review. I cannot find it, but let me keep looking. Oh, anyway, you have to simplify. I just do not want to simplify. I already got into triangle. Fine. Maybe I made them up. So now you do integration with respect to y. Everything gets even worse. And then you simplify.
There was a question about why looking for the volume.
Let's see.
In the chat.
Why do we care about the volume? I have lesser answers. Let me see which one should I use. Answer number 1, the exam problem will tell you find the volume, and then your job is not to get lost in the terminology. They will say find the volume below this object above. That means a double integral. If you have a question about like why do you in general care about volumes, I mean, you want to know how big things are. That's one point of view. Volumes also can represent, like I mentioned, temperature, density, aerodynamics, waves, signals actually accumulate together into volume. Even so the radiology kind of studies, they use it a lot. Even weather involve winds studies. See, it's too late for me to remember this. So when you have storms, which by the way create some snow right now somewhere around Texas, right? I don't think they had snow after all, but seems like they were supposed to. So these things that swirl and create tornadoes and stuff, those are all vector fields. And then they get together and accumulate the volume, which is not the typical volume of the box, of course, right? It's a more wind volume with the pressure inside squeezing things and stuff. So that is also should be calculated using double or even triple integrals. Triple integral might take into account the force, and the force is usually stronger over here than over here. That's why if it catches the house at the edge, it usually stays and survives. But if it catches the house over here, it breaks into pieces. So that's, I guess, a couple of answers. Hope it answered the question. Yeah. No, that's a good question. I was just thinking several things I know, at least. Now let's finish the stupid question. Your question was too good. Whatever we're doing right now is not that interesting. Y cube over 3 minus, it's going to be 4 over 4 minus 5. Oh, that thing. 1 plus y cube over 3, but divided by 1. That's U substitution over here. Do you remember the substitution? I'm testing my calculus 2 students on Tuesday on U substitution. Y cube over 3 minus, well, actually it's plus 5y to the 4 over 4. Look at that, I'm good at this even when I'm sleepy. So my English gets worse, but my math is still okay. Interesting. I noticed a long time ago. 0 and 2, and finally you plug lots of 2s and zeros. 0 kills everything except this guy actually will survive. And then 2 will give you some number, okay? And this number is a volume. So your job is to know how to integrate double integrals, at least some. Let's see. That means we should move on to hard stuff. This is going to be interesting. Okay, so like brace yourself. This is going to be good. I'm good at explaining this. So let's try to push this harder. And then you see also control maps are coming, that kind of stuff. What is the volume? Or they just say, calculate this integral over d y cubed dA, where d is a triangle. Треугольник. That's how you say it in Russian. Triangle region. Треугольник. Triangular region with what kind of? With vertices. Vertices. 0, 1, 7, 0. And this problem I see in front of me, so I should not mess it up. Okay, good. So what is happening here? What I wanted to point out is that this, again, is a completely outside function. Let's call it z or f. I like calling it f. You don't touch it for like a while. It's there, but that doesn't have to do anything with you figuring out what are the limits of integration. And that is somehow the most complicated part of this problem. So let's do that. Solution. Check out how I explain this. So like I explained, there's a 3D object f, which is y cube. It's still a 3D object floating in the space. Above x and y axes, above 2-dimensional. It's floating in the air. So it's floating above the triangle region, actually. So we should kind of draw a triangle. Triangle has vertices 0, 1. Let's not mess up this. 7, 0, and 1, 1, like so. Okay, that's a nice looking triangle. So there is a curtain above this triangle, and they're asking us to find volume below the curtain and above the triangle. That is double integral. So our job is to figure out what are the limits of integration of here. They might be all numbers, or they might be not all numbers. And that's kind of the bad case because it's hard to figure out. From 0 to 1, from 0 to 7, and this is 1, 1. Very good. 2 cases. We learned type 2 and type 1. I called case 2 and case 1. Let's do it like this. Case 1. Do I explain it nicely? It's a very good note here. Type 1 is the one that will have dx at the end. So order matters if you have functions, and that's why they never gave you the order, because you can choose now or figure out what the order will be. In this case, the order was dx dy. Sometimes you can switch it, sometimes you cannot. You can always switch them if all of the limits of integrations are numbers, then order doesn't matter. There's a theorem explaining it. But if even some of them, even one of them is a function, now you cannot easily switch it. You have to learn how to do it properly. It's like U substitution kind of situation. So case 1 is dx being outside. That means they will be double integral with dx outside, which means dy is inside some function f, doesn't care, doesn't matter which is that, in black color, and then in green, I'll put it in red, outside, we choose dx. That's the one we got used to from calculus 1 class, having dx to be outside. Why I'm saying it? The function outside will have numbers at the limits of integration. So outside, they're always numbers, remember that. Because only this way you can get a finite number as the answer. If there are functions outside, the answer will be a function, but volume is not a function in this specific case. It's supposed to be a finite number, 17 cubic centimeters or so on. So it's going to be from A to B. X is going to be from A to B. Y might be from a function to a function or from a number to a number. But what matters is while X is from a number, that's my notation for the number, to a number. And you know, smaller number and bigger number, so that will be easy on the x-axis. Y will be from a top function, and I noticed in my notes I made a mistake about the order. Of course, top function goes higher, and then bottom. I just do top and the bottom. Moreover, it will be written in the form y equals, y equals, y equals. That's the one we got used to from calculus 1 class. So that's the one more natural for our brain, just because we got used to it. So that is case 1. That is good. I would write down y equals top and y equals bottom, like so. That represents a scan. Imagine there's a CAT scan. You're putting a piece of leaf and the leaf is scanning it like so. On the x-axis, it's scanning it from A to B, just like this. It's scanning from A to B, from A to B, which is like sound. And then it becomes a rectangle. That's too much. So to make it actually the shape of the leaf, for example, I put a leaf to see the skin like so. It's a leaf. Now it scans too much. To scan the shape of the leaf, it will scan from the top function to the bottom function, like so. It will look like this, top to bottom, top to bottom, top to bottom. This double scan now gives me the shape of the object. I should say the hand. Hand will be more interesting, actually, but it doesn't matter. This is case 1. Let me briefly explain case 2, which is more complicated for us to understand somehow, because human beings are very good in seeing top minus bottom kind of thing, but somehow it's not very good seeing right minus left. Who knows why? So if you choose the integral to end up with dy, then y will be from a number to a number, c to d, on the y-axis. So now the scan goes up first, from c to d, like so, up, 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 from small to big. Now x, dx part, will be a function, and now it will be x equals. And instead of top and the bottom, since we already scanned top and the bottom, we scanned up already, it will be scanning, actually the same leaf will work. The same leaf with blue and green. It will work like so. It will be scanning from the right to left, from the right to left, from the right to left. So the function on the right minus the function on the left, let me write it down. X is now going from the function on the right to the function on the left. Y is now going from a number to a number, C to D, like so. And there's some kind of stupid function inside. Nobody cares what it is. That is like the last step actually to actually integrate it. So the complicated job is to build this stuff. Let's do the example. I was explaining all of this, but actually there was an example over there. Let's figure out this triangle with vertices. So we build a triangle. Let me rewrite it again. And now they are asking us, how does it look? Up? Okay. No, 1, 1, 1, 1. 7, 0, 1, 1. It's not the, it's like that. Yeah, I think. Yeah. So, like so, 1, 7, 1, 1. Yeah, it looks like so. So which case is that? And you're like, well, let's try the case. So you can choose right now. That's the thing. And sometimes both work. Like for this example, actually, both will work. Top and bottom, right and left, both are going to work. Sometimes it's one example is easier than another example. In class, I would ask and make a long pause and wait for people to think. Right now, it's just too time consuming. Let me explain to you. If I do example number 1, this function is at the top, and then it switches to another function to be at the top. And that's why it's complicated. You'll have to break it into 2 cases. It's going to be case number 1. This is going to be case number 2. And that's why example number 1 is not a good, case number 1 is not good for this scenario. For this triangle, right minus left works very good because there's always one function on the right and there's always one function on the left. So this is actually case number 2. Case number 2 is double integral with dx outside dy outside. Y is going to be, we agreed, from a number to a number because outside function should end up to be with a number and number. Y is from 0 to 1. It's height. It's literally height. Height is from 0 to 1. That is the easy part. And now the hard part starts. The x is here, and x should be from a function to a function. The x is coming from this line. X equals blah, blah, blah. And then to this line. So from the line on the right to line on the left. And don't forget, there's a stupid y cube waiting inside. That is not important for now. And now the whole process starts. You have to build those lines. You need to remember how to build. So step 1, we chose the case. That's actually the most important. The most annoying one now is to actually build equations of the right function and left function. These are, remember we were teaching you equation of the line through 2 points, or you can find the slope, for example. There are different ways of doing it. For example, in my notes, you can see, let's do left one, L. Well, I somehow called it L, but it's on the right. That's so dumb. Let me rename it. For example, the one on the right is this one. The one on the right goes through the points 1, 1, and 7, 0. You can find the slope. Minus 1, 6. You know how to find the slope? It's going to be 0 minus 1 and 7 minus 1. That's minus 1, 6. And then you have a point. So it's going to be y minus, choose any point. For example, 0 equals the slope x minus 7. That's the formula if you want. You have mx plus b formula also works. So this line is minus 1, 6 x plus 7, 6. This is the line on the right. Unfortunately, we don't need it in the form of y equals. Luckily, we know how to solve for x. That's why we took pre-calculus class. X is minus 6y plus 7, because if you remember, dx means x equals should be for each side of the limits of integration. Left one goes through the points 0, 1 and 7, 0. And then you do the same thing. This will be y equals minus 1, 7x plus 1. Rewrite it. X equals minus 7y plus 7. Put it in the box. Finally, we can now step 3. Integrals from 0 to 1 in terms of dy, but the x is different. X is going from right to left. Function on the right is minus 6y plus 7. Remember, it's x equals. Function on the left is minus 7y plus 7. Finally, now it matters that the function inside y cubed. And you start integrating just like I did right now in the previous example. The outside function waits. The inside function is integrated with respect to x. So it's going to be x y cubed. Bar, you plug minus 7y plus 7. Minus 6y plus 7. Where to plug? Well, remember, you integrate with respect to x. So you plug into x. So here. And then finally, going to integrate with respect to y. So the top minus the bottom, blah, blah, blah. Integrates, simplify. It will be y to the 4 dy. So y to the 5 over 5. That gives you 1/5. Yeah. To remember right minus left, top minus bottom, I'll scroll back in a second. I wanted to add, it's always going to be for the one that is a function, not a number. It's always going to be larger, minus small, from larger to smaller for x and y, larger and smaller. That helps a lot actually to understand it, because it's always the one at the top, right? It's larger than the one at the bottom. So it goes like this. The one over here, the one on the right is larger than the one on the left. So it goes like this. So the one that has functions always obeys the same idea, from larger to smaller, from the roof to the floor, from the, what is on the right? From the cat over the snake to the tail. So yeah, you should expect this one on the exam because it's from homework. David is correct. I did not create exam, but I saw that they just picking up it from homework. And this one has lots of stuff to practice in it. So like that. Move on. Oh, sometimes they will give you partial credit sometimes. I saw it like this. They will ask you this kind of question for partial credit. So there's the integral from A to B, integral from C to D, y cube. And for example, they already chose it for you. And then they will ask you, so what is A, what is B, what is C, what is D? So at least you will not mess up with these guys. These guys usually are straightforward. And that gives you partial credit. 0, 1, function, like so. How about just working with the graph? Example number. That was a long example. 10. That was a long example. Example number 10. So what if we just give you the graph? You certainly homework probably. This one. Like so. Shape. And it's not a triangle. It's some kind of other shape. In this case, trapezoid, right? Cube. And a line, whatever this line is. And they say, figure it out. What is going to happen here? You will have double integral, and then you choose. This one actually works both ways, right to left, always function on the right and always function on the left, or top and bottom. There's always one function on top and one on the bottom. So for this example, I think they chose it for you. They decide, you know what? Here's dx dy. What are your A, B, C, D? So X is easy. Again, remember, numbers go outside. X is from 1 to 10. It's literally the width on the x-axis from 1 to 10. So you got points for that. You figure out there's some kind of function here. Y is from the function to a function now. Y is from the function the top and the minus function the bottom. It's always larger minus smaller. So in this case, it's top and bottom. The function at the bottom is actually a number. Well, it's not a number, it's still a function. It's y equals 2. So this one will be easy. It's just y equals 2. The function at the top is a line that goes through 2 points, 10 and 7 and 1 and 10. And you repeat the whole thing, basically. You build the equation of the line through 2 points really fast. Find slope, 7 minus 10 over 10 minus 1 should be negative because it's going down. Build the line, put it in here, done. I believe in you, you can do it. Okay, leaf example, I explained it. There was one really tricky problem on the test from this chapter. And I was like, no way. And it was asking, is this picture A or picture B? And I was sure I was correct. And then I checked the answer and it was not correct. And I stuck for like 10 minutes. And then I found the catch. It was a negative sign. And like, are you kidding me? This is the meanest thing to put on a test. So I deleted it. I got so angry. I deleted it. I was like, no way, if I messed up when it was not an exam, how you guys expect students not to miss? There was like a negative sign there. Of course, it flips the order. I'm like, screw this. I just got angry. There's still 12 questions, but at least it's not in the pool of questions anymore. I deleted, I changed 3 examples. One was not fair. It was not in the homework at all. I did not recognize it. I looked through it, the whole homework, and I did not see it anywhere. And it was not easy. So like, that's not fair. I also deleted it. And then, before I move on to those beautiful drawings I have over here, I wanted to mention this volume under, volume. Find the volume under some function z, x squared plus y squared, over, and then they give you this weird notation, which maybe you never seen before, but actually, we do teach it very early in high school, American high school, I don't know, but we do teach it somewhere in school. And it's just it's kind of unusual to see what is going on. But you should see the difference between this notation is x and y, while this notation is x1 and x2. y1, y2. It's kind of the separating apples from oranges. That's the English phrase, yeah? So this is kind of 5 apples and 17 oranges in the backpack. Here it's like the range of apples from -5 to 0, the range of apples from 10 to 50. That's what they do. And this product here means that this is a rectangle. So you need to build a rectangle like so. And x is from -5 to 0, and y is from 10 to 50, and then you repeat the whole thing. Why so many oranges? Actually, I just went to Sprouts and got lots of oranges. Oranges are good in winter. They also super tasty. Very good vitamin C source. And if you have sugar addiction like I do, you should try to eat more oranges. It's supposed to substitute crave for sugar. So integral dx dy with the function. That is the answer actually. Volume equals, right? Function inside. Doesn't matter here. All of them will be numbers, and that is the only case where you can easily switch the order of integration without thinking about it. So y is changing from, you don't even need to graph, from 10 to 50. X is changing from -5 to 0, or x is changing from -5 to 0, 10 to 50. In this way, it doesn't matter. The answer will be the same. You can check it yourself. Only when they are numbers, you can change. Actually, almost done. Very good timing. I have only a couple of things left to show. Couple of things left. 12. Also, people asked to share this PDF file, which is, of course, I'm going to share. 12. Graphs. Well, let's call it contour maps. Is it you? Contour. It's too late for me to remember. Contour, right? Maps. I should check. Contour maps. So, yes, thank you. I was waiting for someone to tell me. So I'm just ignoring. Yes, thank you. See, thank you for being nice. So let's see. Did you figure out those problems? I'll show you right now. They are horrible. Nobody likes them, to be honest. Nobody likes those problems. There's a cross, and they were like, well, do you understand what this means? Like, la, 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 and this thing over here, and this thing over here, and there's a circle, and then there's this thing. And all of them have numbers. So it looks super fancy, basically. Basically reminds cartography, right? The study of maps. And then there's a weird circle over here, which is 1. And then this circle is -6, and -5, and -4, and -3. And then there's also numbers. I color coding them for no reason, just not to look weird. And there's like thing over here. Who knows what it means? -1, and 1, and 1, -1, and then 0, 0, 0, 0. And you have to like have 5 glasses to even see what is going on. And you have to like zoom in, and then they say, do you see maximum here? Sure. Of course I see maximum, and so on. So let me explain you how to do this. I took time and learned it a couple of years ago. Contour maps, actually, it's a pretty interesting idea, but just it's annoying in the homework and on the test at the same time. Anyway, when you see cross like this, that's the saddle point. So it's nice to know that, at least that is fast. Do you know why? Because idea of being maximum and minimum at the same time matches here. So it's like from this point of view, it's maximum, and then from this point of view, it's minimum, and so on. It's like in my example actually doesn't look like that. But, oh no, it makes sense. You see, numbers are heights on the mountain. The height is 0, then goes down to -1. And then there's a 1 here. Yeah, goes up to 1. So it is minimum and maximum. So what is this? Is it a valley or it's a mountain? It's both. And because it's both, land navigator, very good example. Because it's both, that is the saddle point. Let's call it O. It's usually 0, 0. O is a saddle point. Saddle point. Just remember, it's both maximum and minimum. From one side, it's maximum. From another side, it's minimum. I show you how the balls were falling down or staying on it. So, yeah. And now this, what is happening with this point? Let's call it B. What do you see? What do you think B is? Let's see. On the level B, you are at -6 level. But right behind it, it's -5, and -4, then -3. Is it getting higher or lower? Lower. What do you think? Well, okay, I just let you know. -6 is the lowest one, right? -6 is the smallest number from -5, -4, -3. And it means it's minimum, at least local minimum. Makes sense? So it means if you drop the ball, it will go down to -6. It will descend, gradient descent. Finally, how about the red color thingy? Let's call it C. It matches. Let's call it something funny. Let's call it F. Yeah, that's a Russian F, and also it's 5, so it's a good name. F. or phi. So in the circle, so the circle is still part of the green, actually. It's like over here. This is the circle. In this circle, it is 1. Then it became -1. Is it done? Yes. Then it became -2. And then -3. So at the level 1, are you standing at the top or at the bottom? Seems like you're standing at the top. So if you drop the ball from this circle, it will go down, down, down. So that's maximum. Max. That means it's already 2 hours long since my tablet is done. Maximum. And I should probably turn off this. Oh, that's exactly what I showed you. See? Saddle point. Yeah. So that is good. See, it's doable, just kind of annoying. And don't forget to zoom in the graph. Finally, the last thing I wanted to show was polar coordinates. You will start them soon. Well, the sooner you start it, the better. Not too bad, actually. People like polar coordinates. You will not believe me right now when I say it, but somehow it's actually not as bad as, what is going on? It's not as bad as Cartesian coordinates. Cartesian coordinates, actually, to be honest, are pretty horrible. That's why other coordinates were created in the first place. Just a little bit of thinking. Oh, okay. That was very slow. Okay, hold on, baby. You're almost done. I know it's super hot already. Now it's getting crazy. Polar coordinates. Polar coordinates. So I'll teach you the way to memorize it. It's really good. What you need to remember about polar coordinates is that x squared plus y squared is r squared. Yay, we remember this from Calculus 2 class. And you should remember that tangent of theta is y over x. But the most important is definition. Definition is that x is r cosine theta and y is r sine theta, like so. That basically will be a huge part of all your homework and so on. And I will teach you how to go fast. What you need to remember is the formula of converting from Cartesian coordinate into polar. And those are the examples you will have in your homework and on your exam. So Cartesian, also called rectangular coordinates. For example, convert integral over d. The function is e minus x squared minus y squared dA. Convert to polar. Polar. If we know, what do we know? That d, if, okay. I would say where d is the region bounded by, let me make this, okay, let me make a hard one so you have easier later. 4 minus y squared and y-axis. Okay, y-axis. That takes you to Calculus 2 class. We were doing this bounded by, oh, this is bounded. BDD is a very nice English notation for bounded. I like it a lot. The first thing you should notice is this. Minus x squared minus y squared is minus r squared. The best thing you will see is those correlations. Horrible things like square roots, more square roots, and squares in Cartesian are just small short notations in polar, and that's what it was created for. It was created to use these correlations because here's a circle, and the circle is called x squared plus y squared equals r squared, where r is the radius of the circle. R is the radius And this one is circle centered at 0, 0. So very good. So you see, minus x squared minus y squared is minus r squared. Boom, we already shrinked e to the blah, blah, blah to minus 2e to the minus r squared. It already looks better, you have to say. Formula has, actually, I don't have to erase. Formula, when you read the formula thing, has one additional thing that does not come out from understanding. It comes from the theorem, which you don't have to know. But there's a theorem that tells you how it was all created. And you should remember that from Cartesian, when you jump to polar, there's an extra r shows up. Then it will be dr and d theta. So we're converting, double integral. We are converting from dx, dy, and sometimes dz into dr, d theta, where it's a circle. Those are polar coordinates. To be honest, that's not a new topic. We do teach it at the end of Calculus 2 class because of this Calculus 3 class. Polar says instead of Cartesian coordinates where we have width and height, run and rise, run is x, rise is y, we will do it that each point is actually r units away from the 0, called pole, and then angle will be with the positive direction. With the positive direction of x, the angle will be called theta. So each point, x and y, will be converted into how far I am from the pole, what kind of angle I do have with the x-axis. So if you get lost, that's how I teach in my classes. If you get lost when you hike, you can tell people your coordinates, either in x and y. You can say, I remember I walked 7 miles to the west and then 15 miles to the north. Or you can say, I walked 7 miles away from the base, and I think I was keeping this angle of like 45 degrees because it was towards the mountain. And this will be the unique location they will find. So that box will give you unique. Anyway, my point is that this R, people get confused about this. R comes from the formula. You just need to memorize it. That is to memorize. Memorize. And then my friend made a very funny, nice memorization tool, which I love. I just found it last semester. I just memorized, but now I learned how he did it. And now I teach it the same way. It's a pirate formula. Pirate. Why? Because it's integral. Do you get all my class now? Keep saying it in class. It's very funny. 100 people. And like, do you guys remember? It's integral e to the minus r squared and what? And all people in the class are like r, dr. And that's how you remember that there should be r there. If you forget this r, you mess up the whole formula. So I kind of like it a lot. Now let's put what is actually happening, limits integration for this r dr. They told me we need to draw this picture. So this polar understanding actually is not relatable to the problem we're talking about. The problem we're talking about right now has its own picture. It seems like, no, you just ignore, okay, fine. Seems like it's here, x equals a square root of 4 minus y squared in the x-axis. Let's draw this instead of just a circle. Well, actually, x squared equals square root 4 minus y squared is a circle. It's x squared equals 4 minus y squared, right? If you square both sides. Then it's x squared plus y squared equals 4, but it is a circle. Radius 2, don't forget it's not 4, right? It's radius 2 squared. The only thing is, why did we even bother to have square roots at the first place? The square root at the first place tells me that x have to be positive or 0. X cannot go to the negative sign. So that thing means that x can go to the left. That leaves me only the upper half, right half of the circle. That matches, it says x-axis. And x should be positive or 0. So it's right half of this circle with the center 0, 0 reduced to. Let's finish it. It's very simple. I should not say simple, but I just want to encourage you. You can understand it fast. It is good enough for a couple of days to do. Theta is the angle. The angle which you can see in front of you is from minus pi over 2 to pi over 2. You can ask me why we don't use 3 pi over 4, those angles. Stick it from 0 to 2 pi and make it symmetry also helps a lot. So it's from minus pi over 2 to pi over 2 because the formula says that theta should be from 0 to 2 pi, like so. And then r, you remember, it goes in the order. The function outside is theta. Theta is from minus pi over 2 to pi over 2. R is the radius. It comes from 0. R is from 0 to a number. Oh, technically speaking, infinity. I should not write this down. R can be any number. So the circle can be as huge as possible. In this case, the circle is restricted to 2. So R is this from 0 to 2, from 0 to 2, from 0 to 2. And this is how it fills in the whole circle from 0 to 2. And you integrate now. This integral will be done using U substitution, by the way. This is U substitution for you to know. R, you choose minus R squared to be U. And then dr will be 2r, dr, dr. And then you finish integration. It's in my notes, so you can figure it out. You know, checking my notes, and let me do one more, and then you will see it's one more example. Yeah, why not? Paraboloid stuff. Let me check. Any questions? No angle identities are needed for the exam. We will have to know the level curve pictures based on formulas. Like when they ask us what picture go with what formula. No. I made sure it's not there on the test. The contour map and homework is that's true. So under the paraboloid, so I'm saying contour maps might be on the exam, but at least you don't have that complicated matching situation. What is the hyperbola matches with what and evenly spaced and so on. Yeah, there was one weird problem I did not like. I also deleted it with contour maps. I think it's way too many ways to mess it up. Polar coordinates, volume, this and that. So let me give you this one example. Sometimes it's just the whole circle and it's even easier. Iterated integrals are not going to be easy, unfortunately, but at least this one, I will just do one. I just made it up. Yeah, why do even bother? It's easy actually to make up good examples for polar, like so. Check it out. Example 2 for polar, which is last one. 13, lucky number, 13. Yeah, that's going to be a lucky number. One more, you have integral and integral, and then you have x squared plus y squared raised to the 3 halves, dx, dy, let's do it, dA, d, and d is circle. Circle centered at 0, 0. Radius 7. Boom. This is a very easy example. So I kind of like these examples a lot. Look at that. Look at that. Even if you never seen this topic before because you did not start 12.3, you can see that I'm right. X squared plus y squared is r squared. Nobody wants to integrate this weird x squared plus y squared to the 3 halves. But using amazing polar coordinates, it becomes super simple to integrate because it will be r squared raised to 3 halves. 2 and 1/2 cancels out, so it's just r cubed. And we know how to integrate r cubed. And that's why polar coordinates were created to deal with spherical rotational processes and shapes. It's easier to integrate there than in Cartesian, because circle in Cartesian can be have to be expressed in the plus minus square root situation. It's plus minus square root describes circle in Cartesian, which rectangle coordinates. But in polar, and soon you're going to learn cylindrical ones, it's so much easier, and that's why we created this in the first place. Now let's draw the picture. Here is, I should make it pretty this thing. A nice picture of this sphere. Oh, circle, of the circle. Here it is, centered at 0, 0, radius 7. Radius 7. What is the formula for that circle? Well, it is x squared plus. How will you describe it in terms of the radius and theta? Well, radius is changing. The smallest radius you can find is 0. The biggest radius you can find is 7. What about the angle? Well, the angle, the smallest angle for the point starts here. That is 0 angle. So I will not put it here. That's degrees. And then goes around and ends up to be at 2 pi. Theta is from 0 to 2 pi. Boom. The integral becomes, this is d. So the integral becomes r cubed. You get how I got r cubed? It's r cubed. And then 1/2 cancel out was 2. dA. dA is now, guess what? Who wants to say? R d theta. So polar has to have the r d theta. The moment you see the r d theta, your memory should tell you, wait, I forgot the pirate thing Julia told me. So then you add r with it. R d theta. Okay, you don't forget that part. It's very important. You'll get 0 on the problem. You might do everything correctly except this one little mistake. So don't do it. Actually, after this joke, none of my students forgot R. It's so funny. Previous years, they would forget. And then with this joke, they stopped forgetting it because it's just a funny, good joke. It's a pirate integral. And I will tell you a funny joke about pirates in a second. So then the theta is standing outside. Then theta is from 0 to 2 pi. Nice. R is standing next to it. So it's going to be inside the integral. R is from 0 to 7. Very nice. Integrate. R to the 4 in R to the 4. Integrate with respect to R. Will be R to the 5 over 5 from 0 to 7. Integrate that from 0 to pi over 2 d theta. That is going to be 7 over 7 to the 5 over 5 times 2 pi. Ask me, do you know how I got this so fast? Times 2 pi. So if you have an empty integral, like so, with like a constant outside. So there's some kind of constant standing outside. And in this case, it's 7 to the 5 over 5. Empty integral gives you the length of the interval you're integrating over. I'm integrating over the interval from 0 to 2 pi over 2. So that will be times 2 pi. That's how I know. That makes it faster this way to figure it out. So that's how we usually do it. In general, if you have integral with numbers, then you can integrate it separately like so. It's integral from 0 to 2 pi. And there's no function in terms of theta, so it's empty. And this is 2 pi. By definition, this is area below the graph, which is 1 over in x-axis 0 to 2 pi. So it's just length from 0 to 2 pi. That's 2 pi minus 0 kind of situation. Times integral from 0 to 7 r to the 4 dr. So based on the properties, if limits of integrations are numbers, you can break one integral into product of 2 integrals and then calculate each separately. So What I don't remember lots of puns because foreigners don't get English puns. It's a very high level of knowledge to understand a joke and then English kind of part of it. But I know the pirate pun. Let me see if you get it or not. What is the, you should write in the chat your answer. Is there still anyone here? What if I'm talking to myself? Oh no, lots of people here. So type in the chat. What do you think is the favorite pirate letter? Favorite pirate? How do you? So did I say it in the last class? Yes, people usually say it's R because also it's RD theta, but it's this C, right? So that's a good one. I like it. Oh, you saw it in my videos? Did I mention it? Yes, I mentioned in the class. People really like this pun, so now I like using it. So I'm very proud that I know it. And the other pun I learned is if you pour root beer into the square glass, it becomes beer. That's the other one I remember. Okay, I think that was very good. Questions in the chat. Ellipsis domain. Ellipsis domain. No, I know what you're asking about. No, I did not see ellipsis domain. Squares. No, we don't do squares in polar. So usually spheres and usually some kind of spheres. It can be upper half. If there's an upper half of the sphere, like so, then y will be a square root of 4 minus x squared, because y now have to be positive. That's how you know. And that's how usually people remember. If it's y equals a square root, y have to be positive, so it's upper half. If it's x equals squared, then x have to be positive, so it's right half. If it's minus, then guess what? It's the lower half. If it's minus for x, then it's left half. So that kind of makes sense, to be honest. And that's why it's not convenient. In Cartesian coordinates, a circle is these two together. So you have to integrate each other separately. It's just not good. And that's why spherical coordinates and polar coordinates. Polar coordinates right now and spherical coordinates in exam 3 are very good. Of course, after this, we go into 3D, and all of this becomes a sphere. Add the volume to this thingy. Now it's a sphere, and you'll be learning spherical coordinates. Okay, you guys, I think it's good enough for the review. And stop.